Good morning. Today let us study about angular momentum operators. What are angular momentum operators? What is angular momentum? Angular momentum is very important. Very important. For example, rotatory motion of the molecule. Angular momentum is due to rotational motion of the molecule, rotational motion of the particle or any object. For example, there are two types of momentum. You have studied momentum, there are two types. Linear momentum, that is in classical, we know from classical physics, the linear momentum is equal to mass times the mass of the particle, velocity of the particle. Okay, so this is the linear momentum and this is the angular momentum. There are two momentum. If there is the angular momentums are important, and as I said, for example, electron revolves in an orbit. Electron revolves in an orbit with radius vector r, and it gives orbital angular momentum. Orbital angular momentum. Okay, therefore, this is, and similarly, the electron spins about its own axis. Electron revolves in an orbit and also spins about its own axis. That gives spin angular momentum. So the angular momentums are very important for studying rotational spectroscopy, electron spin resonance, nuclear spin resonance spectroscopy, etc. So the angular momentum operators are very important. So let us see. This is the linear momentum represented by P, and where capital L is the angular momentum in classical physics, and M is the mass of the particle. The corresponding term is moment of inertia. In linear momentum, it is I, mass, the corresponding term is I. Similarly, B, corresponding term I. Therefore, P equal to mB, L equal to I into omega, where I is equal to moment of inertia, I equal to mr square, and omega is the angular velocity, Okay, so let us now derive the kinetic energy expression for the angular momentum. How do you derive the kinetic energy? You know, the kinetic energy is equal to 1 by 2 mv square. From classical physics mechanics, we know the kinetic energy is mass times the square of the velocity of the particle. Okay, now corresponding term mi. Okay, in linear angular momentum. This is linear momentum in angular momentum I and omega square. Okay, so here you see this is a particle moving in a circle, or it is moving in a rotatory motion. Therefore, this is the radius vector, okay, and this is the velocity vector, that is momentum vector, and you will see we will come back 1 by 2. Now let us derive the kinetic energy operator for rigid rotator. For example, when a molecule is rotating with the fixed distance, the internuclear distance is constant, it is not changing. Therefore, the kinetic energy of the rigid rotator, why it is called rigid rotator? Because the internuclear distance is fixed. Okay, this is useful for studying rotational spectroscopy and microwave spectroscopy. Therefore, kinetic energy operator equal to, now you multiply numerator by I, denominator by I, both numerator and denominator by I. Therefore, you will get I square omega square divided by 2I, and I omega equal to L square, that is divided by 2I, L cap square divided by 2I. This is the operator for the kinetic energy of the angular momentum. As I said here, L vector, that is the angular momentum vector, is perpendicular to the R vector and the linear momentum vector. Remember, from classical physics we know that the angular momentum vector is perpendicular. For example, R vector is in the direction of x, and the momentum vector V is in the direction, momentum is linear momentum is in the direction y, the angular momentum is in the direction z. So the angular momentum is mutually perpendicular to the radius vector and the p vector, therefore it can be represented L vector equal to r vector cross product of p vector. R vector, the radius vector is defined as I vector x plus j vector y plus k vector z, p vector equal to I px, px, py, pz are the linear momentum components along x-axis, y-axis and z-axis. Okay. Now L vector equal to, therefore this can be written as I j k vector, therefore x, y, z and px, py, pz. Therefore we can get that L vector equal to I vector Lx plus j Ly, and Lx equal to Lx and Ly, Lz are the angular momentum components along x-axis, y-axis and z directions. Therefore x, for example Lx equal to ypz minus zpy, and similarly Ly equal to clockwise, therefore zpx minus xpz and Lz xpy minus ypx. Okay, now we need the L cap square to obtain the kinetic energy of the orbital angular momentum or spin angular momentum. L cap square. What is L cap square? L vector dot L vector. Therefore, you know that L vector. Therefore, Lx square plus this vector squaring, you will get Lx square, L cap square, y square, L cap z square, I vector into I vector dot I vector equal to 1, j vector j dot j equal to 1, k vector dot k vector unit. They are unit, I, j, k or unit vectors. And now let us find out the operator expression. Operator for angular momentum, angular momentum along x-axis and y-axis and z-axis, therefore Lx cap. We know that from previous operator we have already studied. Please see the operator video, the operator class. Px cap equal to minus I, h cap equal to h by 2 pi dou by dou x. Okay, dou by dou x is partial derivative, with respect to x. Differentiation with respect to x, p cap y equal to minus I h cap dou by dou y. Similarly, p cap z equal to minus I h dou by dou x. Now you can substitute the operator expression in this classical equations, classical expressions. Therefore, Lx cap x equal to y and pz minus I h cap dou by dou z minus z minus I h dou by dou y. Therefore, you can take out minus I h cap as common in both the sides. Therefore, y dou by dou z minus z dou by dou y. Similarly, L cap y equal to minus I h cap z dou by dou x minus x dou by dou z. Similarly, L cap z equal to minus I h cross bracket x dou by dou y minus y dou by dou x. Okay, now we have derived this. So we have obtained the angular momentum operators, L cap square, and also the angular momentum operators along x-axis, y-axis and z-axis. Now let us see the commutation rule, and also we have already studied what are commutators, what are non-commutator operator so please see the previous operator video. And L cap z square comma Lx, it means the square bracket commutator. The two operators commutate. If the two operators are commutative, then equal to 0. For example, L cap square comma Ly L cap square, Lz are all equal to 0. That means the two operators are commutative. The two operators are commutative. That means L cap square and Lx can be simultaneously measured. L cap square, Ly can be simultaneously measured because the two operators are commutative. If the two operators are commutative, then they have the same eigenfunction. They may ask in your competitive examination. Similarly, what are non-commutators? For example, Lx, Ly, you can evaluate the, for example, Lx you know and Ly you know. Therefore, A cap, B cap equal to A cap. In the previous class, we have seen A cap, B cap minus B cap, A cap. We can evaluate and show that it is not equal to the commutator. The two operators are non-commutative. That means not equal to 0. Similarly, Ly, Lz minus L cap x not equal to 0. Therefore, cannot be simultaneously determined. For example, position and momentum operator are non-commutator. They are not commutative. Therefore, position and momentum cannot be simultaneously determined according to Heisenberg conservativity principle. Now let us apply eigenvalue equation and obtain the angular momentum eigenvalues for L cap square and L cap z. Where A cap psi equal to A psi according to the postulates. This is nothing but eigenvalue equation. Similarly, L cap square operates on a wave function for orbital motion of the electron, and the psi is a wave function used to describe the motion of the electron, describe the orbital motion of the electron, equal to, and the eigenvalue and into psi. Therefore, the L plus 1 H cross square is the eigenvalue or the eigenvalues obtained by solving this eigenvalue equation. Okay. Therefore, the L equal to 0, 1, 2, 3, etc. and L cap z operates on a wave function psi. It will give ML H cross psi, ML H cross for eigenvalues for the linear for the angular momentum along the z direction. Angular momentum along z direction. These are the eigenvalues obtained by solving the eigenvalue equation, and ML equal to minus L through 0 to plus L. Okay, they will ask the angular momentum operators are very important for studying rotational spectroscopy, rigid rotator problem, and also electronic spectroscopy, because UV visible spectroscopy, because electron moves in a circular orbit, they will have angular momentum. And also in any competitive examination, they will ask the values whether the two operators are commutative or non-commutative, whether they can be measured simultaneously or not. So please understand and try to solve the problems. Thank you for watching.